What if the equations were correct, but the physics was wrong? Not wrong in calculation, not wrong in prediction, wrong in what they were actually describing. That question sounds strange. It probably should. In the early 21st century, the standard position among physicists was that mathematics and physical reality were essentially the same thing. That if an equation worked, if it produced accurate predictions about measurable phenomena, then the equation was not just a tool. It was a window into the structure of the universe itself. We are looking back at this now from a distance of approximately 75 years. And what we observe is not a civilization that was foolish. What we observe is a civilization that was extremely early. A civilization that confused the power of a map for the territory it was mapping. This transmission is a retrospective analysis of a specific and consequential transition in human understanding. The period we are examining runs roughly from the 1920s through the early 2000s. It is the period during which theoretical physics became increasingly and then almost exclusively mathematical, during which abstraction became the primary mode of scientific inquiry, and during which a particular question was quietly set aside, treated as either unanswerable or unnecessary. The question was this: what is the mathematics actually made of? To understand what happened, you need to understand what physics looked like before it became fully mathematized. In the 17th and 18th centuries, natural philosophy, the discipline that would eventually become physics, was deeply committed to mechanism, to physical explanation. When Newton described gravity, he was troubled by it. He produced equations that worked with extraordinary precision, but he could not explain the mechanism. He could not say what gravity actually was, how it propagated, what it moved through. His famous phrase, hypotheses non fingo, I frame no hypotheses, was not a philosophical position. It was an admission of incompleteness, an acknowledgement that the map existed but the territory remained obscure. For roughly 2 centuries following Newton, physicists held this tension in productive balance. The mathematics was powerful, but the expectation remained that a mechanical explanation would eventually follow, that someone would find a thing underneath the equation. That expectation began to dissolve in the early 20th century, and the dissolution was not forced by failure. It was triggered by success. Quantum mechanics arrived, and it worked better than anything before it. And it came with a warning embedded in its foundations that most people chose to treat as a feature rather than a problem. The warning was this: the mathematics of quantum mechanics did not describe a physical reality that existed between measurements. It described probabilities. It described what would be observed. It was silent, structurally silent, about what was actually happening when no one was looking. The Copenhagen interpretation, which became the dominant framework for understanding quantum mechanics for most of the 20th century, essentially institutionalized this silence. Do not ask what the particle is doing between measurements. The question is not meaningful. The mathematics is sufficient. That was the moment, that specific intellectual move, repeated and reinforced across decades of successful research, trained generations of physicists to accept the mathematics as the explanation rather than as a description. And then something followed from that acceptance, which was almost invisible at the time, but is quite clear now. If mathematics is the explanation, then more mathematics is better explanation. If the equations are not just describing reality, but constituting it, then the project of physics becomes the project of finding the most complete, the most elegant, the most unified mathematical structure possible. This is not an unreasonable inference. It followed logically from the premises, and it produced genuine progress in the middle decades of the 20th century. The Standard Model of particle physics is one of the most precisely confirmed theoretical structures in the history of human science. Its predictions match experimental results to extraordinary decimal places. It is, by any measure of predictive power, a triumph. But look at what it does not tell you. It does not tell you why those particular particles exist. It does not tell you why the constants have the values they do. It does not tell you what a quantum field actually is in any physical sense. It gives you a mathematical object called a field defined by a Lagrangian, and it tells you that when you calculate correctly using this object, you get accurate numbers. It stops there. It was designed to stop there. Stopping there was treated as intellectual maturity. We are recording this now because that stopping point, which felt like the stable floor of modern physics, turned out to be a suspended platform. There's a concept in the epistemology of science called underdetermination, the idea that a given set of observations is always compatible with more than one theoretical framework. That data alone cannot uniquely determine which theory is true, only which theories are consistent. Early 21st century physics encountered underdetermination at a scale it was not prepared for, and it responded in a way that is instructive to examine. By the early 2000s, the leading candidate for a fundamental theory of physics was string theory. String theory proposed that the most basic constituents of reality were not point particles, but one-dimensional vibrating strings, existing in 10 or 11 dimensions, most of which were compactified, curled into geometries too small to observe. The mathematics of string theory was genuinely extraordinary. It was consistent in ways that competing approaches were not. It connected to gravity in a way that quantum mechanics alone had never managed, but it produced something alarming in the process, something called the landscape. The mathematics of string theory did not yield a single universe. It yielded something on the order of 10 to the power of 500 possible universes, each with different physical constants, different particles, different laws. The mathematics was so rich, so flexible, that it could accommodate almost any set of physical facts. And that, quietly, was a problem. A theory that can explain everything explains nothing in the way that matters. A map that contains all possible territories is not a map of the territory you are standing in. What happened next is what concerns us here. The community did not abandon the framework. It adapted its standards. A concept called the anthropic principle was deployed with increasing frequency. The argument was essentially this: we observe the physical constants we do because if they were different, we would not exist to observe them. Therefore, the observed values require no deeper explanation. They are selection effects in a vast multiverse of possibilities. Now consider what this means epistemologically. It means accepting that the question of why the universe has a specific physical structure it has is unanswerable in principle. Not unanswered yet, unanswerable in kind. The mathematics could generate all possibilities and observations selected from among them, and that was a complete account available. Some physicists accepted this. Many were deeply uncomfortable with it, but the discomfort did not produce a major reorientation of the field's direction. The mathematical program continued. The investment was too large. The community was too committed. The careers, the institutions, the journals, the funding structures, all of them had organized around a particular conception of what physics was supposed to be doing. And that conception had, quietly, become difficult to question without appearing to be anti-scientific. Here is something worth holding in mind as you consider this history. The difficulty was not scientific. The difficulty was sociological. The mathematics worked. The predictions were confirmed. The researchers were skilled and sincere. But a subtle epistemic boundary had been drawn around the field, and most of the traffic moved within it rather than questioning it. The question that was quietly unavailable was the one Newton had originally posed. What is this actually made of? Not mathematically. Physically. What is it? We should be precise here about what we mean when we say that physics became too mathematical. We are not arguing that mathematics is the wrong tool. We are not suggesting that equations are misleading or that quantitative reasoning is suspect. The mathematical tradition in physics produced achievements that stand as genuine monuments to human intelligence. What we are examining is something more specific, the way in which mathematical consistency became a primary criterion for theoretical acceptability, sometimes displacing physical interpretability entirely. The way in which the question of what a theory was actually saying about the structure of reality was treated as somehow less rigorous than the question of whether the theory was internally consistent. Consider the measurement problem in quantum mechanics. It remained, across nearly a century of intense activity, genuinely unresolved. The mathematical formalism described quantum systems evolving according to the Schrödinger equation in a smooth, deterministic, linear way. And then it described a different process, collapse, happening at measurement, which was discontinuous, irreversible, and not captured by the same equation. The two processes did not fit together. They lived in the same theoretical framework, but the seam between them was never properly closed. Multiple interpretations were proposed across the decades. The The Copenhagen interpretation, many worlds, pilot wave theory, relational quantum mechanics. Each of them attempted to supply the missing physical account. And here's the striking thing. They produced identical predictions. Experimentally, they were indistinguishable. The question of which interpretation was correct had no empirical resolution. And so, officially, the question was set aside, treated as philosophy rather than physics, as a matter of taste rather than science. But the question was asking something real. It was asking, what is the measurement problem telling us about the structure of reality? What does the existence of this unresolved seem imply about the completeness of the framework? Is it possible that the framework is an extremely good approximation of something else, something deeper that the mathematics is not yet capturing? From where we transmit, we can see that the answer to that last question was yes. But we will not state what was found. That is not the purpose of this transmission. The purpose is to show you the shape of the uncertainty that existed, so that you can feel the weight of what was being assumed. There was another dimension to this that deserves attention. It is a question of physical intuition, and what happened to it as the mathematics became more abstract. The physicists who built the foundations of 20th century physics, Bohr, Heisenberg, Schrödinger, Dirac, Einstein, were all deeply committed to physical understanding as a goal. They argued fiercely about what their mathematics was saying. The Bohr-Einstein debates, which stretched across decades, were not arguments about who had the better equation. They were arguments about what reality actually was. Einstein's discomfort with quantum mechanics was not a failure of mathematical ability. It was a commitment to the idea that a complete physical theory should describe what was actually happening, not just what would be measured. He lost that argument, at least in the sense that the Copenhagen framework became dominant. But the argument itself was a sign of health. It meant that physical interpretation was still understood to be the goal. As the decades passed and the mathematics became more sophisticated, the expectation that a physical interpretation should accompany the mathematics became less standard. Graduate training in theoretical physics increasingly emphasized mathematical facility, the ability to manipulate the formalism, to perform calculations, to derive results. Physical intuition was still valued, but it was harder to teach, harder to test, harder to publish. This created a subtle but consequential feedback loop. The researchers who succeeded were increasingly those who excelled at formal manipulation. The questions that were published were increasingly those that could be posed and answered within the existing mathematical frameworks. Questions that required stepping outside those frameworks, that required asking what the framework was actually made of, were harder to phrase in ways that journals would recognize as physics. The boundary between physics and philosophy of physics became more strictly policed, and the traffic moved almost entirely in one direction. We want to pause here and be direct with you about something. There is a belief, fairly common in the early 21st century, that the progress of physics was essentially complete at the fundamental level, that the remaining questions were either technical details awaiting more powerful accelerators or mathematical refinements of existing structures, that the major conceptual work had been done. This belief was not held universally. There were dissenting voices. There were physicists who argued loudly that the foundations of the field were less secure than they appeared. Lee Smolin, Roger Penrose, George Ellis, and others made sustained arguments that something was wrong with the direction physics had taken, that the mathematical program had run too far ahead of its physical foundations, that a course correction was needed. These arguments were not ignored, but they were, for the most part, absorbed without altering the field's primary trajectory. The standard answer was that the dissenters were asking the wrong kind of questions, that their concerns were philosophical rather than scientific, that science had to continue with the best available tools, and the best available tools were mathematical. What none of these perspectives, neither the mainstream nor the dissenters, fully anticipated was a role that a different kind of intelligence would play in reframing the question entirely. We will not elaborate on that. The details are not yet yours to have. What we will say is that the reframing, when it came, did not invalidate the mathematics. It contextualized it. It placed the equations within a larger framework that made their extraordinary precision comprehensible in a way that had not been comprehensible before. And when that happened, several things that had seemed like permanent mysteries turned out to be readable. The measurement problem resolved. not by choosing one interpretation over others. By finding what all of them had been approximating, there is a pattern in the history of science that is worth naming explicitly because it recurs across domains and across centuries. A tool that works extremely well tends to become, over time, the definition of the domain it was designed to serve. The map becomes the territory. The method becomes the subject. The language becomes the thought. In physics, mathematics was a tool. It was not chosen arbitrarily. Mathematics had proven itself as a language in which nature's regularities could be most precisely expressed. The successes were real and accumulated across centuries. By the 20th century, the relationship between physics and mathematics had become so intimate that it was natural, almost inevitable, to begin treating them as the same thing. But they're not the same thing. A map is not the territory. A shadow is not the object. A pattern is not the medium in which the pattern occurs. This distinction, which sounds simple, is extraordinarily difficult to hold in practice when the map is extraordinarily accurate, when the shadow matches the object to 17 decimal places, when the pattern is so stable and so universal that treating it as a fundamental thing seems like the obviously correct move. And yet there is always, in principle, a question available beneath the pattern, a question about what the pattern is a pattern of, a question about what the regularity is running in. That question is not always productive. There are moments in the development of knowledge when it should be set aside in favor of more tractable problems. But setting it aside permanently, treating it as unanswerable in principle rather than merely difficult in practice, has a cost. The cost is that you become very good at the map and you forget you are holding one. We want to consider one more dimension of this before closing the analysis. It concerns a relationship between mathematical beauty and physical truth, and the assumptions that were made about that relationship in the period we are examining. There is a principle that was widely influential in theoretical physics, most closely associated with Paul Dirac, that a physically correct theory should be mathematically beautiful. That elegance was a guide to truth, that the equations governing reality should, at some level, be aesthetically satisfying, not merely technically functional. This principle produced real insights. Dirac's equation predicting antimatter was derived largely from a demand for mathematical symmetry, and it was confirmed. The mathematical beauty of gauge theories turned out to reflect genuine physical structure. The connection between symmetry and conservation laws, captured in Emmy Noether's theorem, is one of the deepest and most productive relationships in all of science. But the principle is also used increasingly as a criterion in situations where experimental confirmation was not available. String theory was, and still was in the early 21st century, judged in part by its mathematical beauty, its internal consistency, the elegance of its structures, the richness of its connections to other areas of mathematics. And here the feedback loop completed itself in a particular way. If mathematical beauty is a guide to physical truth, then the more beautiful the mathematics, the more confidence one might feel about the theory even in the absence of experimental confirmation. The mathematics itself became a form of evidence, and that was a subtle but significant shift in what physics was. Beauty is a human perception. Elegance is a function of the cognitive tools doing the perceiving. What seems beautiful from within a particular mathematical tradition may look different from outside it, or from within a different tradition, or with different cognitive apparatus than the one that produced a judgment. We do not say this to diminish the genuine aesthetic achievements of the mathematical tradition in physics. We say it to note that beauty, as an epistemic criterion, has limits that were not always acknowledged. Some of what seemed beautiful turned out to be correct. Some of what seemed beautiful turned out to be a local optimum, a summit from which the larger mountain was not yet visible. What do we mean when we say that physics became too mathematical? We mean something precise and something careful. We mean that the field developed a systematic preference for mathematical tractability over physical interpretability, that questions which could not be posed within existing mathematical frameworks were treated as not yet scientific, rather than as invitations to develop new frameworks, that the criterion of experimental confirmation, which had historically been the discipline of the field, was relaxed in domains where experiments were not yet feasible, and that mathematical consistency was allowed to substitute for in ways that were not always announced as substitutions. We mean that a generation of exceptionally talented researchers spent significant portions of their careers on theoretical structures that were beautiful and consistent and, ultimately, incomplete descriptions of something they had not yet fully characterized. And we mean that this happened not because the researchers were confused or careless, but because the institutional, social, and epistemic structures of the field had converged on a particular mode of inquiry that was very powerful in certain domains and quietly insufficient in others, and that the insufficiency was difficult to see from inside the mode. The people working within early 21st century theoretical physics were not limited by their intelligence. They were limited by their tools, their frameworks, and the social structures that organize what counted as progress. These are limits that affect every civilization at every stage of development. They are not embarrassing. They are structural. They are the condition of being early. The reorientation, when it came, did not arrive as a refutation. It arrived as an expansion. The mathematical structures that had been developed across a century of extraordinary work were not discarded. They were placed. Their precision was explained. Their limits were located. The question of what the equations were made of, the question that had been set aside for so long, turned out to have an answer that made the equations more comprehensible rather than less. We will leave the content of that answer where it belongs, in the future that you are moving toward. What we will say is this: the thing that was missing was not a more powerful equation. It was a more precise account of the relationship between the mathematical description and the physical reality it was describing. A clearer understanding of what it means for a pattern to be real, of what it means for a regularity to exist in something. Physics was not wrong. It was working at the level of the shadow, without yet having the tools to examine the object. And the shadow was extraordinarily precise, more precise than any previous civilization had managed, which is why it took so long to notice that it was still a shadow. The pattern you are living inside is real. The mathematics that describes it is real. The predictions are accurate. And there is something beneath all of that, something that the mathematics is describing the behavior of, which you have not yet fully characterized. That something is closer than it appears. The people who find it will not be the ones who abandon the mathematics. They will be the ones who remember to keep asking what the mathematics is actually about, who treat the equations as the most precise letters ever written, while continuing to ask what the letters are trying to say. Certainty is not the destination. It is a rest stop, a place to consolidate before the next question becomes visible. Early 21st century physics was very good at the rest stop, very comfortable there, very skilled at the consolidation. The next question was already present in the foundations of quantum mechanics from the beginning. It was there in the measurement problem. It was there in the unanswered question about physical interpretation. It was there every time a physicist said the math works and left the sentence there without completing it. The math works. That is true and extraordinary. The math describes something. That is the next sentence. And the sentence after that is the one that changes everything. You are not at the end of physics. You are at the end of one kind of physics. The next kind is already waiting in the questions you have learned to call unanswerable. Signal stable. Archive updated. Transmission paused.